Sweet.
Okay, I'll also post all recordings online and slides, so you can just look. But that doesn't mean you can stop having class. So please go, don't be that. Okay, so some logistics, right? So we're gonna be here for now. We're gonna try and find a room in CSE, which is a little better ventilated, has more light, but for now it's gonna be here. It'll be Monday, Wednesday from 11:30 to 1. And I'm the instructor. Jacob, who's right there, is our TA. We'll introduce ourselves in a second. But I'll have 2 hours of office hours, one on Friday, one on Tuesday. In my office gets 2:15. And Jacob will have 1 hour of office hours on Tuesday. Maybe we should move that to Wednesday, just to like avoid an overlap. Sure. Okay, but we'll post them on EdSTEM and on our website, so should be. Okay, so the grading we're going to do is pretty easy. We're going to do 35% for our final project. The final project is going to be open-ended, and we'll talk about that in a second. We'll have 15% for a new thing we're going to try, which is called a seeded idea discussion, and then 45% for your homeworks. There's going to be 3 homeworks. They're programming assignments. And then 5% participate. You know, if I haven't seen you all order, right? So we'll do most of our communication through EdSTEM. I'm very bad at email, so EdSTEM is the easiest way to reach me, or showing up at my office. Either of those work, but email also works. And we're going to have a mix of lectures and some seated idea discussion. So it'll be a bunch of lectures, and then we'll have a seated idea discussion where all of you participate. And then we'll have a bunch of lectures and idea discussion all of you participate. So, and then finally, I was thinking we should do final projects in a poster session, but we could also do it in like a different format. So what do you all prefer? What should we do? We could do a poster session, or we could do like a lecture type format where we each present for 5 minutes. What's better? Poster. Okay. Yeah, poster is great. And yeah, please participate, because otherwise you're just going to hear me talking and talking and talking. It's going to be boring. Please ask me questions, you know, at any point. Stop me if you have any lazy objections to anything I say. And yeah, let's keep this interactive. Yeah. Any questions about the grading format?
I have a question about your recording. Do we have something also on a report?
So I think it's technically on there. But I'm like pretty loose about it. So if I'd say like, let's make a game time decision in like early December. Depends on how we're feeling. Like it's going to be graded very loosely anyways, and so it's not a big deal. I just want us to have a coherent piece of work to show. I think the poster should be enough, but yeah, we'll maybe decide early December. Is that okay? Okay. So for the project, we have like 3 check-ins, mostly for the purposes of helping you structure class projects, because it's not like a guided project, it's an open-ended project. You have to propose the idea and you have to execute on it and kind of write a poster or a final report. So the hope of the project proposal check-in and a milestone report is just to help you like provide an opportunity for us to give you feedback, right? And so they're not really graded. We're not going to grade them very harshly. We just grade for completion. But please do, submit them. Otherwise, it's going to be hard for us to provide you feedback. And so we'll do one in mid-October, which is just your project proposal. And we'll do one mid-November, which is a milestone report, just to make sure you're making progress. And then the final report, we can either do a final report or posters. Yeah. But just to make sure we're on track. Okay, so what is the expectations for a project? Really, it can be anything that is in the realm of optimal control or reinforcement learning. Right? So it could be something like a new algorithm. It could be re-implementation of an existing algorithm and a set of interesting new questions you ask, right? Like questions about performance, questions about stability, questions about design decisions you're going to make. You could have an empirical investigation, so you have like an algorithm, you want to study how it behaves on certain types of environments or with certain types of rewards or with certain types of function approximators, right? So you like have our fancy algorithm, you want to try it with the transformer, and you want to like study how it scales with size, right? Like that is like a reasonable scope. Or you could even choose a new application in your domain. I know lots of you are from other domains, and so you could try choosing a new application or domain, and that's totally fine, right? But try to think of it this way: we're just trying to get you to learn how to do research, and like there's no point really gaming the system here. Just like think of it as an opportunity for us to help you learn how to do research, and everything else is like loose. Yeah, questions? Really, we're going to grade on just like basically effort and like showing that you've like done a series of steps that are logically consistent. But we won't grade on like project success, you know. Research works sometimes and it doesn't work sometimes. So we'll, sorry folks. So we won't really grade on project success, just on. Cool. Any questions about the project? And we can do it in groups of 1 to 2. If there's an exception where you want to do groups larger than that, talk to me. We can make that. But 1 to 2 is usually good. Yes.
Is it intended that it's separate from like our individual research?
No, I would highly recommend just use your research. If you can reinforcement learnify it, then it's great. Yeah, just like have some connection to the course material. And then I'd recommend using your own research. It's great. Cool. So that's the project. Right. So there's this new format we're going to try called these seeded paper ideas. So last year we did these paper discussions, and I think they weren't that successful, mostly because we were presenting old work and like some of it wasn't that good. But I was thinking, you know, Jacob and I were trying to think about this yesterday or 2 days ago, and we were trying to think about a new format for discussions. So let's brainstorm about it. But basically, we were thinking that we want to teach you all how to do new research in reinforcement learning. And so what we're going to provide you is a seed paper. Let's say it's like a foundational paper that someone else has written, right? And then what we want you to do is take that foundational paper, find the gaps around it, and suggest a new idea, right? So in groups of 4 to 6, we can have you all take a seed paper, find gaps in that paper, new ideas around that, and then kind of suggest a new idea that could be a new paper. And obviously, we're not going to run the experiments, but we want to like go through the process of formulating a research idea, right? And then kind of like go through the process of presenting it in a compelling way to your colleagues, and then kind of like defending your idea to your colleagues in a constructive manner. So we're thinking that we'll give you a seed paper and you have to suggest a new idea. It doesn't have to be wildly novel. It just needs to be a new insight based on that seed paper. So we start with motivation. You tell us why we should care about your idea, why it matters. Then we'll talk about your technical idea. What is the technical change you're going to make? Then we'll talk about some experiments. And you don't have to run the experiments. You have to tell us what are the experiments that you would run and like why are they important. And then tell us how this positions itself in the related work, right? Like there's like a whole body of related work. Maybe you can get them from the seed paper or look around on a scholar. But tell us how this like new paper you're going to present, how does it fit in the landscape of the related work? And so the hope is that like whenever, you know, we come up with a new idea in research, we kind of go through a process like this anyways. You like read a bunch of papers, you find some gaps in the literature, you present why we should care, present some experiments, make a plan, right? And so the hope is that we can kind of go through that as an exercise based on topics in the class. What do you all think? Two out there? Do we go back to normal paper discussions, or does this seem like something worth trying? Thoughts? Yeah? Yeah? Okay, it's going to be an experiment, so it might be a little chaotic, but it'll be fun. It'll be fun either way. And everyone who isn't presenting, like so I think we're 36. So we'll try to make 9 groups of 4 and then do like 3 presentations 3 times in the quarter. And everyone who isn't presenting can like post a commentary on what they thought was cool or interesting about the papers or the ideas that were presented, right? That's all that's done. Only rule is just don't be an asshole, you know, just kind of be nice. That's it. Be constructive. That's the only rule. Questions? Like again, you're not going to be graded really on how amazing the idea is. You know, we're still learning how to come up with ideas, but we're going to be graded on like completeness, effort, you know, willingness to discuss. Those guys. Yeah. Questions? No. Okay, great. So then there's going to be homework. I find that reinforcement learning is hard to understand without coding a little bit. And so we're going to do a couple of different homeworks. We're going to have 3 homework assignments. And they'll be all in Python. Everyone familiar with Python? Yes? Okay. So there will be 3 homeworks. First is on imitation learning. So if you all have been following the news, imitation learning is real hot right now. And so we're going to learn how to imitate experts in simulation. So we're going to test out a bunch of different imitation learning algorithms first. Then we'll go to like simple model-free reinforcement learning algorithms. So algorithms that don't build a model of the world, that learn through trial and error, right? So we'll have policy-graded and actor-critic algorithms. And lastly, we'll have model-based reinforcement learning, where we try to build a model of the world or a world model. You can grab this one if you want, or that one, either way. There's one up here. One right there. I'll try and move us to a bigger classroom for next. Okay, so the third one is going to be model-based reinforcement learning, and that's more like world models that get closer to optimal control. And then we will submit things through Canvas with a small report. They take in the order of maybe 8 hours, maybe less than that, 6 to 8 hours at most. They're like meant to be pretty simple. And like, I guess, I know a lot of you we're at lots of different levels. And so we'll have like in relatively easy homework and then some more difficult extra credit. And so whoever wants to like implement these algorithms from scratch will give you a blank slate and you go crazy and show us what you learned. Good. Sweet. All right. So who am I? So as I said, I'm Abhishek. I'm an assistant professor at CSE. I was born in Oregon. Then I went to India for 10 years, got the accent, got the culture, came back to Berkeley. I did undergrad at Berkeley. I did grad school at Berkeley. And then I was at MIT for a quick 1-year postdoc. And then I've been here. And so what I'm mostly interested in is reinforcement learning and its applications to robotics. And so reinforcement learning is a useful tool for things like games and recently for LLMs, but I think there's relatively less success in robotics, but there's lots of promise of success. And it's a great place to do research. And so what we're trying to think about is robots that keep getting better as they spend longer in your homes, in your offices, in your factories, right? And so yeah, that's kind of what I'm interested in, but I'm also interested in like machine learning more generally. How do you think about robustness, generalization, optimization, etc. So any of those things that seem interesting to you come down. Outside of work, I used to do tennis, but now I'm old, so I do pickleball. That's great. Do soccer sometimes, and yeah, we're running out of hockey soon, so that's exciting. Yeah, Jacob, do you want to go?
I'm sure.
Sorry.
I'm Jacob. I'm currently in the BS Economics program, master's student in CSE. My kind of trajectory is I was born in Seattle. I joined the robotics team in high school, and after that I was sold. So I've been doing robotics ever since then. I've been out of stuff for another 2 years, I think. And I'm kind of mostly interested, I would say, in like robotics like in real world. So I really think it's like interesting to like robustify like robotic systems to like make them like not just like have a bunch of hacks and work like actually work. So along that lines, I've done reinforcement learning. I've worked on a systems paper currently working on like some retrieval for imitation learning. But more broadly, again, my interests are more like in robotics and like making them robust. Outside of work, play hockey. I love skiing, climbing. I read by slide violins. I have a dog. I also love dogs, and I like reading and all kinds of games and card games.
Sweet. Thank you, Jacob. And then we ask, who are you? It's not meant to be an existential question. It's more of just, we should just go around and do introductions. So maybe we can start from there and maybe say your name, what year or department you're in, and one fun thing you did over summer. Go ahead.
Hello, everybody. I'm Nicole. I'm an undergrad in the CS department right now. And one fun thing I did this summer was go to China.
Hello, my name is Rohan. I'm an undergrad in the ACMS department. And one fun thing I did this summer was go to Utah.
Hi, my name is Ayush. I'm a undergrad in the CS department, starting the master in snow sweater. And one thing over the summer was I went to the line side. I'm second year in a master's student in mechanical engineering. And I did.
Oh, nice. Awesome.
I'm Kevin. I'm in the BSMS program. One fun thing I did over summer was went to Lebanon.
Nice.
Hi, I'm Anant. I'm a final year PhD in CSE. One fun thing I did in summer was in Chancellors.
Good.
Yeah, I'm Mohammed. I'm third year PhD student in the AA department. One thing I did in the summer, I circled around the entire world. Mostly I went to Europe, then Middle East, then Thailand, and then come back to here.
Oh, yeah. Very good.
Hi, I'm Yuhan. I'm the second year PhD student in the AA department, and I went to the mountain engineering in summer.
Yeah, I'm Ray. I'm an undergrad in CS, and one fun thing I did this summer was go to China.
I'm Gui Liangjun. I'm a second year of master's student in mechanical engineering. Fun thing I did in summer, I play a lot of soccer.
Nice. How'd you go to mid?
I'm at my ECE PhD student, and one fun thing I did was forage for psilocybin.
I'm Gil. I'm an exchange student. I'm from take my master's in machine learning. This is my first year. I have one thing. One fun thing I did this summer was I went to
Hi, my name is Claire. I'm a first year CS PhD student, and one fun thing I did this summer was play Tour de Montblanc, which is like a 10-day long.
I'm Shubham Mittal. I'm from India, and I'm starting this quarter as a master's in the first year of mechanical engineering. And last summer I did a track, 10 days track in northern part of India, and also I also learned driving.
Nice.
Yeah, hello everyone, I'm Isco, and from the department, and a second year master's student. And one thing I did in summer is interesting, the athletes over 3 times a week.
Awesome. Cool. Very
Also a second year student in Sweden. One fun thing I did in summer is I watched 4 concerts.
amazing. Awesome.
Hey, I'm Julie. I'm second year PhD in Nokia and technology. I went to Britain for the summer.
Amazing. Good.
I'm Jake. I'm a fourth year PhD student in the biochemistry department, and summer I played frisbee.
Hello, I'm Jack. I'm a BSM student in the CS department. And one fun thing I did in summer is I got into golfing, and it's really interesting.
Right.
A quick question though, when they were saying the AA department, what is it? Or EE, they were saying. Or
Who was saying?
Something we're saying they.
Oh, Aero Astro, yeah.
Oh,
You can take this one if you, or maybe, is that one taken? Cool. Alright. It's a dialogue from. You want to introduce yourself?
Sure.
Yeah. Yeah.
Hi everyone, I'm David. I'm a master's student in PhD. One fun thing I did this summer was go to Los Angeles, was actually Disneyland.
Oh, awesome.
And I went during the heat wave, so there was no one there. I managed to go all around.
Very
Hi, my name is Lenny. I'm a computer science student. I'm here like for an exchange from ETH in Zurich. I'm a master's student. And the fun thing I did this summer was I went to campaign at ETH for Australia.
Awesome.
I'm Oscar, I'm a PSMS student and did this summer.
Hi, I'm Hamish. I'm a second year PhD student in NLP. One fun thing I did, I went to my first concert at the Gorge and we did
Amazing.
really fun.
Nice.
Very great.
Good.
Yeah, I'm Matthew, a second year PhD student, and I worked remotely from Vietnam all summer on my research.
Wow. I wish I could do that. That sounds good. Go ahead.
Your CS PhD student, and one fun thing I did this summer was I watched my first episode.
Exciting. Go ahead.
Hi, my name is Sri. I'm a fifth year undergrad student in mechanical engineering and computer science. And one thing that I'm still doing is I'm participating in an opera down in Tacoma.
Awesome.
Hi, I'm Tom. I'm a first year mechanical engineering master student. One thing I did over the summer was TK.
Maybe.
I'm Tamari. I'm a master's student in mechanical engineering, and in the summer I got introduced to a couple new board games, which I've enjoyed ever since.
Awesome. Good.
Hi, I'm Rico. I'm a third year undergrad in CS. One fun thing I did over the summer is I got introduced to the game of the Thomas.
Very cool. Go ahead. Okay, nice. We're gonna go back there.
Hi, my name is Thomas. I'm a first year PhD student. And what they did this summer was learn how to make Catalan. History.
You wanna make some for the class? Oh, I got Go ahead.
I'm available. I'm a first year CSE PhD student. One thing I did this summer was I did a pizza tour in New York.
Wow, exciting. Cool. How was it?
Great.
Nice.
Yeah.
Good, Brown.
And interesting things like this was deep water swimming, except climbing where you fall into the water.
Oh.
There's a swimming pool.
Awesome. Yeah. Very cool. But
Hello, I'm Scott. I'm a second year PhD student in vision and NLP. And this summer I spent a few days in the Olympic.
nice.
All right, so I'm Sam. I'm a first year mechanical engineering master's student, and I spent a week routing through the Grand Canyon.
I think it's you, Max.
I'm Saman. I'm a second year chemical engineering PhD student. And one fun thing I did, I also went to the Broad for the first time.
Nice. Very cool. All right, lots of traveling this summer. It's great. Now you're here in the rain for the next few months. It's gonna be great. All right, so let's talk about what this course is about, right? So this course is largely about the design and practice of reinforcement learning algorithms, right? So there's a huge bunch of algorithms that we consider. It's not just PPO, it's not, the only algorithm out there. There's lots of other ones too. And so this is a rough taxonomy a couple of years ago of a bunch of algorithms that we'll hopefully be able to parse by the end of the quarter. Right? But we want to study how do we design different types of algorithms, what are the pros and cons of each of them, where should we apply each of them, and then how do we make them useful for domains like games or robotics, or things like LLMs and so on. Right? So we don't want to just study the theory, right? I think we want to study the design of new algorithms, what went into the design of old algorithms, and how do we study the trade-offs between them. So, we want to get algorithms that are practical, and when you say practical, in some domains, you can collect an infinite number of samples. If I'm playing StarCraft, I spin up 10,000 StarCraft samples, it doesn't matter. If I'm in a nuclear reactor, I can't do that, right? And so the considerations in different problems are different. And so often we think about things like sample efficiency, operating from high dimensional observations like images or even higher dimensional things in science. And we want things that keep improving, right? So we don't want things to saturate. We want them to be convergent. We want them to be efficient. We want them to be broadly applicable. And so reinforcement learning, typically has been applied on things like games historically, but we want to make them applicable beyond games to things like, robotics, LLMs, science, so on, right? So the issue is that a lot of these algorithms, when they were first created, we go to the history a little bit, but they were created under these like strict assumptions that Minsky or Bellman or someone came up with. But the problem is those assumptions don't hold in most problems in the real world. And so we need to think about how to modify our algorithms so that they actually operate under real world assumptions. And as we'll cover in the class, like that leads to certain types of issues in these algorithms. They like are no longer convergent. Sometimes you have requirements that don't hold in the real world, right? Safety becomes a consideration. No one cares about safety in a video game. Like problems like this become real problems. And I am hoping that we can kind of get into those considerations in this class, right? And I know from what we talked about, lots of us are doing different things that outside of CS. So if you have particular considerations you want to bring up in the class, we can try and address those as well. Or see if that should spawn a new research area. Okay, so we want to not just build algorithms that do reinforcement learning, but more generally problems that do sequential decision making, right? So when I say sequential decision making, I mean things that are not just questions and answers, but things that take multiple steps in an environment. We'll formalize that in a second, but that it could include things like imitation learning, model-free reinforcement learning, or model-based learning, which is often called like world model learning or generative model learning. But the hope is that we don't just learn to design these algorithms through your homeworks, and so the class we should learn, which parameters to look for, what should be the things you debug. Like I want to give you the ability to design your own algorithms rather than just like textbook understanding of these algorithms. Otherwise, you could just read a textbook. Right? So the hope is that those of you who've done RL before know that it's like a bag of black magic, and you like have all of this dark knowledge on which things to tweak and which things to clip and which things to initialize to 1e minus 6. And we can hopefully kind of demystify some of those things for you. Well, I don't know the answers to all of them, but I can at least tell you the rationale. Okay, sweet. It's not a theory course. So if anyone's expecting a theory course, you should go take CSE 541 or read this textbook. There will be no sample complexity bounds. Maybe one or two, but no more than that. Okay. Simon and Kevin teach excellent theory courses in CSE. Please go take them. But we'll only cover the theory we need to motivate the algorithms. We're going to try and motivate them in a principled way, but we're not going to do sample complexity bounds. Yeah. And the hope is that after you take CSE 579, we should be able to do things like this, right? We should be able to at least do simulated characters like the ones in Mujoku, like your ant, your half cheetah, your swimmer. Like those should be easy peasy, right? By the end of this class. You should be able to like figure out how to get algorithms to work on robots, be able to fine tune your LLMs with more than just PPO. Yeah, the hope is that we should be able to not just apply things to different algorithms, but also figure out the iterative loop between designing an algorithm, looking at the learning curves, figuring out what's wrong, tweaking your algorithm, kind of going back. And so hopefully your homeworks will have some of that, because we're going to give you the wrong hyperparameters, and then you have to figure out the right ones. And so it'll be a fun exercise. Cool. So that's kind of the course logistics and scope. Any questions before we keep going? Or any things that you want that we haven't talked about?
Something like that, RL is not really used in real application, I guess maybe
It is used in real application, not quite in robotics.
robotics or elements, but are there any other domains where RL is particularly are
I think recommender systems. It's like RL-ish, in the sense that it's like bandits, which is like one or a few step RL. But recommender systems are a big use case. Power grid optimization is another one.
that's used in practice?
Yeah, things like that. We'll cover, I didn't mean to say that it's not used in practice. I meant to say that in robotics, it's not used in practice. But we'll cover a bunch of applications where it is used in practice. So like the big one recently has been LLMs, but there's other ones. But
I've seen RL used sometimes in practice for robotics. So I did an internship at Amazon Robotics, and actually one of the like new ways they were developing or like picking and placing was like they were using RL to like find grasp points on like packages. I think by like
it's almost like a bandit.
yeah, it's almost like a band. Yeah, exactly. First, so it's like definitely useful. It's not at the stage where you can just like let RL teach a robot to walk with no. Well, I mean, you can.
I think another place where it is actually being used is locomotion. So like Boston Dynamics and these kinds of companies are using reinforcement learning for their controllers. But it's a bit niche still.
Yeah.
But I think it's like, I didn't mean to say it's not exciting. I think it's actually particularly exciting because it's almost working, which is a great time to be in a research. But those are the ones I can think of in robotics. It's also used often for hyperparameter optimization. So like you can kind of think of like RL as just it's a particular type of optimizer. So like for big machine learning models, people use like sometimes RL to optimize their optimizers. So like find hyperparameters for big models. Sweet. Okay, so the next thing we're going to do is we're going to try and define what reinforcement learning is, right? And then try to like formalize it. So intuitively, reinforcement learning is using trial and error in an environment to learn a strategy to maximize some notion of reward, right? And so what I want to do is, it's kind of Pavlovian in a sense. You want to like, have an agent that is in an environment. It's interacting with the environment, it's observing the state of the world, it's taking an action. The action transitions you to a new state, you obtain some notion of reward in the process, and you're trying to figure out a strategy that gets you as much of that reward as possible. Right? And so we formalize it in a second, but that's kind of the intuition, right? So you think of it training your dog or training your kid or training your grad students. They're all essentially some version of reinforcement learning where you're presenting some trial and error with your environment. You're trying to learn a strategy, right? Which is not just actions in one scenario, but just a generalizable strategy that lets you maximize the notion of reward. So that's kind of the simplest way I can think of putting it. The important thing here is you're using trial and error in the environment, right? So you're collecting data in the environment. So you're trying to make the system general. So you don't need to know that much about the environment besides having access to sampling in the environment. You should be able to take samples. The hope is that the environment doesn't have to be as restricted as some optimal control methods need you to be linear or need you to be convex or piecewise convex. The hope is that we can learn in more arbitrary settings, so we can reduce the assumptions at the cost of some other things. But the hope is we can make it pretty broadly applicable. The hope is that we learn a strategy rather than actions to take in one scenario. And when we say strategy, that's where machine learning comes in. We're trying to learn a generalizable function approximator that can work in multiple different settings. And lastly, the thing that is most different from things like supervised learning is like supervised learning often has, expert labels that someone provides to you, like the state takes action, or this is your question, this is your answer. In reinforcement learning, it's less about, matching an XY pair that we got. It's more about maximizing some scalar notion of success. In some ways, you can think of it like a loss function, right? But you're saying that you have some notion of success that evaluates what state you're in, and you're trying to maximize that notion of success. The other important thing about reinforcement learning is that it's a sequential decision-making process, which means that it's not that you just act in the world and you're done. You act in the world, influences your next state. You act in the world, influences your next state. And so you can't just take decisions that will work for one state. You have to consider decisions over an extended series of states, right? And so you can't just be greedy, or you can be greedy sometimes. But you have to consider how your actions get you to states that may or may not be good in the future, right? And so that's what makes it hard. Does that make sense intuitively? Right, so the hope is that it's an easy way for our agents to continue improving as we drop them into new environments. There's a question mark next to easy because we wouldn't have a whole course if it wasn't a little difficult, right? But let's try and think about why we should do this process at all, right? So I like this quote from Alan Turing, and his logic was basically we shouldn't try to build something that simulates the adult mind, right? So we shouldn't try to like functionally match the adult mind. Instead, we should try and match the child's mind, which can keep learning. So rather than trying to create something that is like has all the functionalities of an adult, it's going to be simpler to create something which is able to learn new things. And if you can learn new things, then you put that thing in a sufficiently complex environment, and you should be able to get to a behavior that is adult-ish. That's the hope. The hope is that it's kind of like an argument for meta learning. You're not saying let's replicate the functionality like we used to in the 90s. It's instead saying let's replicate the learning algorithm, expose it to enough interesting stimulus, right, or environments or data, and that'll lead to behavior that is complex beyond things that you can code in. Right? So rather than trying to directly replicate behaviors, let's try to replicate the learning mechanisms that we see in humans, or I mean, we're not at humans yet, but like in worms, that's where we're at. But that's kind of, I thought that was an interesting philosophical take on it. Everyone has different philosophical takes on it, but I thought this one was cool. More practical take is I want to build continually improving robots, right? My Roomba, we got a Roomba a couple of months ago. It's just garbage. And I need it to get better. Just keeps getting stuck under the dining table. I don't want that to happen over and over and over again, right? And so we want systems that keep getting better. And so some reasons why I think it's useful for robotics is that you have sequential decision-making problems. Most robotics problems are not one-step problems, right? You care about doing a series of things that lead to good behavior. Robot data is expensive. Those of you who've done robotics know it's a pain in the ass to keep collecting robot data. The world is naturally multitask and continual. It's changing all the time. It's hard to encode all of the scenarios that you might see. And so if you have something that is static, it's definitely going to be outdated in a couple of months. And so you want a system that can keep getting better. And a lot of robotic behaviors, especially for high dimensional robots like hands, are hard to pre-program. Like I don't even know how to pre-program a hand in the world of pen. It's like in many cases, easier to get that out of optimization than it is to program. Right? So that's what makes it useful to have robots that collect their own data to improve. And so, the hope is that we can drop our robots into a kitchen with some amount of pre-training data, let them keep getting better as they spend longer in the environment. Right? That's the hope. Sweet. So I like to provide a little bit of historical context on reinforcement learning. So it started like a little bit diffuse. It wasn't called reinforcement learning. I guess it started with some animal psychology. And so those folks on the left are Pavlov on the top and Thorndike on the bottom. And there's a question on chat. That's Pavlov on the top and Thorndike on the bottom. And Thorndike proposed this thing called the law of effect, which says that if you like enjoy something, you act in a way that you do more of it, right? And Pavlov had obviously this experiment with the salivating dog, but a lot of animal psychology was trying to study conditioned stimulus and unconditioned stimulus and how they're correlated, right? So it's like, how do we explain things like salivating when food shows up or salivating when a bell starts ringing? And how do we exploit that? That for artificial systems came later, but initially they were just trying to study animal systems, right? And that kind of evolved from psychology to neuroscience, where they're studying like how dopamine affected different processes of learning or repetitive behavior. And on the other hand, but these folks were doing psychology, right? And so no artificial systems yet. On the other hand, Bellman and Hamilton and Jacobi were doing optimal control. And so optimal control is like often developed in the context of defense, as many things are. But the hope is that we have a dynamical system that's specified by F, and the how a dynamical system evolves is specified by F. You have to minimize some cost function, integrate it over time. And they like basically developed a series of dynamic programming algorithms, which you'd call Hamilton, Jacobi, Bellman equations, or the Bellman equation, things like that to do optimal control. There's also related to Kalman filtering. For those of you who are familiar with Kalman filtering, like all of that was to kind of control and measure dynamical systems, but no learning, right? It's like known model optimization. You're just trying to find the optimum. And then this idea of dynamic programming or temporal difference kind of brought these fields together. And so a series of folks, this is Harry Klopp, who is a researcher at the Army Research Lab. He like had a bunch of these papers on like how we can design intelligence systems from different pieces which reinforce each other. And so he had this like system, you can go read this paper, it's a little hard to read, but it has a bunch of these different systems which are acting together. And if one system is useful to another, its behavior is reinforced. And you try to like, that was like one of the early algorithms for temporal difference learning. And you probably heard of these folks, Sutton and Bartow. They have a big textbook. You should go read it. But they like kind of took these ideas and made them useful for computer science, right? And so they said, TD learning is great for psychology and it's great for optimal control. How do we make it useful to play backgammon and chess and control robots to some extent, right? And so they kind of brought these things together, and there's lots of other big names who kind of thought about this, but at least that's my understanding of how the history evolved. I'm not that old, but I think this kind of covers how things went. Sweet. So there's also, for those of you who are more brain inclined, there's some interesting evidence on how reinforcement learning happens in the brain and how dopamine connects to reinforcement learning processes. So like initially, the understanding was that dopamine would lead to certain things being reinforced and other things not being reinforced. But I think they're still studying it. But my understanding from my Wikipedia search last night was that dopamine has been kind of correlated more so to errors in prediction. So it's like, if I didn't expect something and then I saw a stimulus I didn't expect, then I would get dopamine to reinforce some sort of behavior. So it's more correlated to errors in prediction than to like stimulus that you like, right? But it doesn't fully explain things. And so for those of you interested, lots of cool neuroscience papers. That's a good survey to get started with from the other. All right, so that's a little bit of history. And kind of the way modern reinforcement learning started was in 2013. Have any of you read this paper? No? It's a great paper. You should read it. Oh, nice. Yeah, so this paper is, it's also called DQN, or Deep Q networks, right? And it's this first example of reinforcement learning working with deep neural nets, right? So there's a field of reinforcement learning, and then we like smashed it with deep networks. And the first time it kind of worked in a reasonable way, I think, was in 2013. Where they like taught these networks to play Atari games. And so they have all of these Atari games. And they said, like, what if we, and they naturally give you rewards because they have a score, right? And so what if we cast this as a reinforcement learning problem and just let agents keep practicing on these games? And they used a variant of Q learning, which we'll cover in the class. But the result was that they were able to like get really, really good performance. It wasn't quite superhuman then, but since then it's become far, far, far better than humans in most games. And then my own start with reinforcement learning is in 2015. So this is John Schulman. So you probably know him. But he used to be a lab mate of mine. And he did these really cool experiments where he was trying to get these humanoid characters to walk. Right? And so he proposed this algorithm called trust region policy optimization, which we'll study in like 3 lectures or so. And the idea was that he wants these continuous control problems. So like Q learning was largely discrete, like you go up, down, left, right, and shoot, right? But continuous control, that's like a 30 degree of freedom system. So how do I get these systems to walk? And so he built these model-free reinforcement learning algorithms, which is kind of the basis of PPO and like a lot of the new algorithms that kind of were able to walk within just a few hours. So I thought that kind of started this space. And since then, we've gotten lots of really cool things to work. So they've gotten some interesting results on using deep reinforcement learning for nuclear reactors. I don't know if that's the best idea, but they've done it. They've done really cool things with AlphaGo and games. So you have pretty high interaction factor games like Go. And with the variant of Monte Carlo tree search and TD learning, you get performance that is really surprising in 2016. In robotics, it's not quite working at the level of production yet, but you get cool behavior like, see, is this a video? No, it's not. Well, this is the OpenAI had a demo in like 2017 where they're able to like spin a cube and solve a Rubik's Cube and do things that we thought were really hard to program with model-based methods. And lastly, most recently, it's been successful in reducing hallucination and getting reasoning into language models. Right? And so lots of cool applications since then, but it started with Atari games. And so, yeah, I think that's pretty cool in less than 10 years. So pretty fast, pretty high impact. So that's exciting. Okay. Questions? I guess I just told you a bunch of facts, so it's not that many questions. But please stop me at any. Okay, so we want to define a formalism, right? So to be clear, there's an agent. Agent is your robot, your neural network, your recommender system. Like it's something that inputs stimulus, states S, outputs action A. The action goes into the environment. The environment is external to your agent. The environment steps to a new state. And the assumption in most reinforcement learning is that the reward magically appears for you. And then you have to just optimize the reward, right? And so the problem definition states that you are going to observe a state. You're going to take an action. The state and actions are defined for you, like what space of states you can take, what space of actions you can take. You will receive a reward, and your goal is to maximize the reward. Okay. So, like, one of the reasons this formalism is insufficient is because actions are a choice, right? Like if I have a robot, I can choose many different types of actions to take. Or states are a choice. I can choose what to input into my model. Or rewards are a choice, right? And so I think when you instantiate this in practical algorithms, those become more of a consideration. But that's the basic formalism. And we're going to try and formalize those using some mix of probability, optimization, and machine learning, which are all like pretty connected things. But we're just going to try and lay down a formalism that we're going to use throughout the rest of the quarter. Yeah.
What's the difficulties that are in robotics compared to games?
Yeah, that's a great question. So the first is sample complexity, right? So it's like data is expensive in the real world. It runs at real-time rates. And so collecting data on a robot, I can't simulate as much. And so like the amount of data I have is like orders of magnitude smaller. The second thing is safety, right? So it's like if I like have a robot, I can't just like bang into the wall. If it's a simulated robot, I can. The third one, which I think is like less obvious, is resets. So like in a simulator, you fall down, you reset, you try again, right? But in the real world, you fall down, you break everything, or you fall down and you can't keep trying. So someone has to babysit your algorithm. And so it's like much harder to like let it run for like 5 days uninterrupted. Rewards are a big problem. Like rewards in simulation are often easier because you know where everything is. Like you have full state of your system. But in the real world, you don't know where everything is in the open world, right? You're in an arbitrary kitchen, you don't know the poses of everything. And so it's hard to even define a reward. Yeah, I think those kinds of things are, and then there's noise, which is different in the real world and in simulation. And so like noise patterns in the real world are harder to predict, be robust, those kinds of things. Yeah.
Do you see like Bayesian optimization as like a subset of like RL, or is like that like completely, and I guess like where you draw the lines?
Yeah, it solves a similar problem, but it solves them with a different set of techniques. So it's also in some sense a zeroth order optimizer in that it like assumes a black box access to your system and tries to find some set of parameters. But it doesn't always have to be a sequential decision-making problem. And it doesn't, it often uses these things like Gaussian processes and so on, which like don't scale with dimensionality the same way, but they offer you better uncertainty estimates. And so for applications like, for instance, like chemistry or things like that, PO is like a great strategy. For things where you have to do lots of sequential decisions, I think reinforcement learning operates, right? But they're like very little. Yeah. You can also instantiate reinforcement learning with Gaussian processes, and then it gets like much closer to that. Cool. Questions? Yeah.
You also have thoughts on how cognitive architecture like so, or I think there's another one about ACTA.
Can you tell me more about it? They're not paging it. And what do you mean when you say cognitive architecture? Do you mean
So
like
you can
ways
historically design, let's say, agents, and then you can create search and planning agents. with
Yeah.
architecture. So
how do they figure into this whole picture?
yeah, and your thoughts on what are their challenges or-
Yeah. So I guess there's two ways I can think of the connection there. One of them is like you can use reinforcement learning to design those kinds of architectures. Because one way of thinking of reinforcement learning is just like a zeroth order optimizer, it's just black box optimizer. So you can like think of them as like there's a whole field of neural architecture search that was a big thing like 5 years ago, where they would like use reinforcement learning to design better architectures for supervised learning, etc. But they weren't doing search and these kind of things. But it could be one thing to design cognitive architectures. The other thing is, right now I haven't really talked about what the agent is, but the most naive thing you can do is specify the agent by just like a feed-forward neural net. But you can also think about using those cognitive architectures as the architectures for your agent. So at test time, it doesn't just like image in, torques out, but it like does some reasoning. And so there's been like lots of cool work on better parameterizations for the agent so you're still learning it with the reinforcement learning objective, but you're using that to train like better architecture that generalizes better. Cool. All right, let's keep going. How are we doing on time? All right, so how many of you are familiar with Markov chains? Right. Okay, so the general premise of a Markov chain, it kind of describes a stochastic process. So you have a series of states, like state at time 0, 1, 2, and 3, right? And so you have a chain that specifies how your state evolves over time. Right? And so your Markov chain is typically specified by some initial state distribution, which says what is the probability that you're in some state, right? And a transition kernel, which says, what is the likelihood that you transition to state J if you're at state I? So it's like a table, right? If you're tabular, it can be a probability distribution if you're not tabular, right? But it's a kernel that tells you how do I transition from state at time t to state at time t plus 1, right? And so the formalism of reinforcement learning largely builds on things that are connected to Markov chains, right? And so why are they called Markov chains? It's because of the Markov property, right? And so the Markov property just says that the future is independent of the past, conditional on the present, right? So if I have the joint distribution of S1, S2, and S3, that means that S3 is independent of S1, conditioned on S2, right? So which means that the current state is a sufficient statistic for the future. You don't need to know the past, right? And so the reason that is good is because for decision making, which we'll cover in a second, you don't need to worry about everything that is before S2. You can just focus on S2 for decision making at time certain, right? And so the Markov property just specifies conditional independence. Right, so when you think about conditional independence, it says if you have a joint distribution, you can factor it as S3 given S2 and S2 given S1 and this one given S0. Right? Does that make sense? It's just all that the Markov property says is that the current observation is a sufficient statistic for the future. So if I need to make decisions about the future, don't worry about the past, just focus on the present. The reason that's important is because it makes like decision making a lot easier because the space of things you need to consider is way, way, way smaller. It's just focused on the present. It's exponentially small. Okay. So point of a Markov chain like Markov chains are often used for different things. Like Markov chains are often used, in chemistry and biology for simulation. Right, so they're often Markov chains are used with these things called Markov chain Monte Carlo. And the goal there is to simulate particular probability distribution.
Question about the independence idea.
Yes.
So if the current decision is only based off of the current observation and nothing from the past,
yeah,
then why would sequential problems be any different from just making decision out of the current?
So let's see. I'm going to try drawing on this and see if it works. So like, let's say I was at this state, right? And now this makes more sense in the context of a decision process, but let's say you were able to take an action, okay? And it affected what state you got to next. The important thing is you can't change the past. The past is the past, right? But you can change the future. And so let's say there was like S4, Sn, whatever, right? And so it's like there might be an S, like let's say there was like many different options for S2. Now, there might be some option that is great for S2, but leads to like duds after that, right? So there might be like plus 10, but after that, everything is 0. Or there might be like a -2, but if you take some more actions, then you like reach 100, right? And so it's like you have to take decisions, not just one step in the future, but considering many steps in the future. So the sequential decisions are in the future, not in the past, right? So it's kind of like, you can't really change the past. Past is the past, right? And so you can only make decisions about the future. But when you make decisions about the future, you cannot just consider the immediate future. You have to consider many steps in the future. Sweet. Okay, so Markov chains are often used for different things, right? So they're used for these like sampling-based methods, but those are not going to be that related until like week 6 of the class. But we really want to make them useful for decision making. And so we're going to define something called a Markov decision process. So it's like a Markov chain augmented with 2 things. The first is action, right? And the second is reward. So if you saw the Markov chain was just state. So it just tells you how the state evolved to the next state, evolved to the next state. There's no decision variables, right? But in a Markov decision process, you have your states, which is telling you where your system is, right? But you also have actions, which determine which state you go to next. And you have rewards, which are telling you how good states are. Right? And so a Markov decision process is typically defined by a state space S, which is different states of your world. Will, like, for instance, where are the objects in your world, or where is your arm, or what are the control variables for your system, right? All of those are your states. You can take actions, which are like, what are the torques on your arm for a robot arm, or do I turn the temperature up or down for HVAC system, right? Any of those things are actions. You got a reward, which is telling you, was this good or bad, right? And then you have the transition dynamics, which we'll call P, right? Or sometimes we'll call T, which is telling you, if I was at state ST, I took action AT, what is the likelihood that I would get to state ST plus 1, right? And so this is typically like a probability distribution, right? So it's not like a 0-1 thing. It's like if I'm at state S1, I take action A1, I'm going to have some distribution over possible S2s, right? And so I'm going to have a stochastic dynamics function, which is saying at S1, take action A1, I get a distribution over S2s. Yeah. The difference from a Markov chain is that you're not just in an uncontrolled system, you're able to choose what your actions are going to be. And if you can choose what your actions are going to be, you can determine what the future will be, right? So you can like take better actions to get to better rewards. Yeah. Sweet. Okay, so, but again, the Markov property holds, right? And so the same property holds as before. So S1, S2, and S3, you have S3 independent of S1 given S2. Right? And why is that important for a Markov decision process? It says that if I have an S2 and I'm trying to choose an action, like I don't need to worry about S1 or S0 because the whole future is independent of the past condition on S2. So if I have a decision-making agent, you can make a decision based on S2 without worrying about S0 or S1. Right? And so when you have the strategy that's trying to maximize your reward, it doesn't need to worry about S1, S0, it only needs to worry about S2. Right? So that's why it's important for Markov decision processes to be Markov, because you like don't need to worry about the past when making decisions. It's going to make life way, way, way easier. And it's going to enable all of these like fancy Q-learning methods that are all going to build on these kind of this independence assumption. Right? Okay. Any questions about MDPs? We're going to use them like constantly. So there are these things called POMDPs, or partially observed Markov decision processes, where the state of the world is not observed. Right. So if you go back to like this thing, we're actually gonna observe S's. So you're gonna always see the states of the world, right? So those are the things you see. But in a POMDP, right? So in a partially observed Markov decision process, you don't see the state of the world. All you see is some observations. Right? So an example is like egocentric navigation. Like I only see what's in front of me, but the state of the world is not just what's in front of me. And so, like for instance, I have limited field of view. If I'm going to take a sharp left, it's like not in my state. And so I actually cannot just make decisions based on my current field of view. I have to consider my history. And so there's a series of problems that need partial observability, but they're harder to solve. And so we'll get to them towards the end of the class, but they're much harder to solve. And the simplest ones are field of view issues. Like if you're an autonomous vehicle, you have to not just worry about what you see right now, but you have to maintain a history of what you saw. And then you have to have like a probability distribution of what the world might be based on all the things that you saw, because you cannot just trust your current observation. And that's much harder. Another one is like for touch sensing, right? Like touch sensing is very much partially observed. Like I don't see something until it touches. And so if I have a touch sensor, I can't just rely on my current touch sensing to tell me the state of the world. I have to think about my history of touch sensing to tell me where the world is. Right? And so for those of you who studied state estimation, like a lot of state estimation deals with this partially observed setting. But we will start by studying algorithms in the fully observed setting. And some of them will extend to the partially observed setting. Okay. So MDPs, it's going to be super important. You'll be lost for like the next 10 weeks if you don't get it. So ask me questions now. It's very simple. It's states, tells you where you are. Actions, tells you how to act. Rewards, tells you how good it is. Transition dynamics determines how one state transitions to the next based on an action, right? And so let's instantiate this concretely for robotics. The state could be something like your camera images, your joint encoders, right? Your actions could be something like how I'm going to move my arm, what my velocities might be. My reward might be, let's say I'm trying to put my kettle into the sink. It's going to be how far was the kettle from the sink, or an indicator was my kettle inside my sink. And the transition dynamics is the physics of the world. Yeah.
Is reward always going to be purely determined by the state?
Either by the state or the history of states. Yeah. So that's the partially observed setting.
Okay.
Yeah.
Other questions?
How about you go on the?
Yeah, the results that use MDPs, do they generalize to like more than one history phase, like you define it?
Yeah, so you can, when you're in these POMDP settings, these partially observed settings, you can always construct an augmented state of the system, which is just a history of the states of your system. And in that case, everything becomes Markov again. But that's like a little, it's almost like trivially silly because it's like you just exploded your state space. So there's like some set of results that will translate from POMDPs to MDPs, but not every result. Right, like so like some examples that won't translate are like for this field of view problem, right? Like the decisions that I would take in an MDP would be like if I like don't see anything, I can take a turn because it's like my current observation is what I see. But in a POMDP, I have to like maintain like a belief state over what the world might be, and then like plan against that. So I have to like make a decision saying, well, there might be an obstacle here, so I can't just like turn left, right? And so that's a different, or you might have to like go and collect more information. So you might say, okay, like I don't know if I'm going to turn left. Let me face left and see if there's an obstacle there, and then I can take a decision. And so the strategy that you would take in an MDP is different from the one you take in a POMDP. Sorry, go ahead.
So the transition, like in robotics, we like the physics.
Yes.
model, because it's a probability distribution, like what is the uncertainty? Like, is it the uncertainty of the knowledge of the physics?
That's a great question. So if you knew if your state was like, you measured every atom of your system, then your transitions would be deterministic up to quantum physics, right? But the problem is you like make these coarse measurements, like you like measure the pose of this thing and it may have some error, right? And so there's some noise from like not observing the state of the system in a detailed enough way. And so you can kind of model that as stochasticity in your system. Or like, for instance, you're like pushing something on that table. If I knew the exact friction on every patch of that table, it would be deterministic, but I don't. And so there's some stochasticity that comes in your system, right? So it's often from unmodeled effects because you have a coarse measurement of the world. Right? But if I knew everything about the world, then I kind of know from physics how the world transitions. Yeah.
Your word is based only on the state, and you have two different actions that lead to the same next state. How do you choose between the two?
It's a great question. So if you're greedy, if you're greedy, they're equally good. So you pick at anyone. But if you're not greedy, you might need two different states which have the same reward. But the further states you can reach from them might be different. Right?
But if they both lead to the same state, and
If two actions lead to the same state, so you're saying like if there's A and there's B, and these two lead to C, right?
yeah, and then there's one before A and B that you choose whether to go to A or
Oh, I see. So you're saying, okay, so like, there's like S, which can either go to A or B and go to C. Yeah, and you're saying like A is like +1, B is +1, C is whatever +10, right? Both of them are equally good under this assumption. Now, the case where they would be differently good is like if this thing goes to E, and this thing goes to F, this thing has +1, this thing has +1, but this thing leads to like bad stuff, and this thing leads to like good stuff. Then you choose that. Okay, sweet. Make sense so far? Are we doing okay? Oh, shit. So POMDPs are similar to MDPs, right? The main difference is that you don't observe the state of the world. You only get an observation of the world, right? So how many of you are familiar with Kalman filtering? Yes, Kalman filters are operating in POMDPs. Roughly not even taking actions, but you're receiving observations of the world. Like you're navigating around a room, you receive some LiDAR readings. The LiDAR readings are noisy. So you have to like integrate noisy readings to get an accurate state of the world, right? So a lot of these algorithms from control are trying to solve POMDPs one way or the other. And so if you want to put your control brain together with your RL brain, like a lot of those algorithms are for POMDPs. And a lot of the algorithms we're going to talk about are MDPs. And we'll extend it to POMDPs in like late November. But there's a lot to study in MDPs. Okay, so the formalism of reinforcement learning is that we have the patient environment loop, and your goal is to learn a policy. So you're going to have a policy, we're going to call it pi theta, and your policy is going to observe the state of your world SC. It's going to go through some computation. That could be a cognitive architecture, that could be a neural net, that could be a decision tree, it could be something, and you're going to output either an action or a distribution over actions. Right? And that's going to tell you how to act in the world. And the goal is for you to figure out what this policy is going to be. The whole like purpose of reinforcement learning is to figure out what this policy pi theta is going to be so that you maximize the expected sum of rewards when you act according to your policy. So a lot of words will unpack that, but a policy is going to take in your state, going to produce a distribution over actions. And the goal is to act using that thing to maximize the sum of rewards. So written in expectation form, it's going to say, you want to figure out the parameters or some parameterization of your policy, right? Those could be the parameters of your neural net. Those could be the like linear weights. Those could be hyperparameters for some control, okay? Such that when you act according to your policy, we'll cover what acting means. You're going to reach a set of states. You're going to measure how good a trajectory was by like, what is the sum of rewards along those states? and you're going to try and say, let's pick a policy where the average sum of rewards is as high as possible. Now, I used a bunch of jargon here. Let's kind of unpack that. So it's going to be a little bit confusing what this means, right? So the trajectories coming from pi theta means that intuitively you can think of it as if you had a controller, your controller is acting in closed loop, which means you observe the state of your system, your policy takes an action, you observe the new state of your system, your policy takes another action, you repeat. And so a trajectory is a sequence of states and actions that you're going to encounter when your policy is acting in closed loop. So your policy is acting sequentially. And then you're going to evaluate how good a trajectory is by taking the sum of rewards at different states and actions along your trajectory. So the rewards can depend on your states and your actions. They often just depend on your states, but they can depend on your actions. Like you might want to minimize the jerk in your robot, or you might want to like take actions that are small, right? So they can depend on both, but your goal is to find the parameters that maximize the sum of expected rewards. Okay, so now silly question for y'all is why expected? Why is it an expectation? Like what makes it, expectations are usually when you have probability distributions, right? So like what is stochastic here?
See, I think it's not deterministic. If it was a deterministic, then we won't have to add expectation.
Okay. So your policy is stochastic. That's a great point. That's one point. I'd argue that even if your policy was deterministic, you'd still need that.
The transition dynamics and rewards are stochastic.
That's right. Your transition dynamics are stochastic. Your rewards are often assumed to be deterministic, but they can also be stochastic. And so typically you want to like average out all those effects of the noise. Right? So this is because of like the stochastic dynamics and your stochastic policy. All right. So the main thing you're trying to learn are the mappings from the states to your distributions of actions. And so your mapping could be something like a table, right? It's just a table which says, like it's a dictionary. I index into a particular state, tells me distribution of our actions. That's the simplest thing. Lots of reinforcement learning theory just does tabular, right? So just like a big table of states corresponding actions. It could be linear, which says that your policy is going to be determined by some linear combination of features of your state, right? If you go back to like SVMs and linear regression, like a lot of them are just linear, and you're trying to learn the linear weights, right? And so the goal there is to learn this W. The goal in the table is to learn the entries of your table. And the goal in your neural net is to figure out what the parameters are of your neural net, right? Or decision trees to figure out what your decision boundaries are going to be. But in all of these settings, I want to be clear that there's two different things going on here. The first is that you are learning a function approximator, and the function approximator is taking in an S. It's going into some function f, or let's call it pi, sorry, which has parameters theta, and then it's outputting the parameters of a probability distribution over actions, right? So it's not outputting just a single action, but a probability distribution over actions, right? So let's say it is a Gaussian. Your policy is going to be outputting the mean and the covariance of a Gaussian. If it's a categorical distribution, it's going to output like a bunch of different logits, which tell you like what is the likelihood of each action, right? And so the point is that there's two things going on. The first is that you have a function approximator that maps from state to distribution over action. And the second thing is that you have to choose a particular distribution over action. So those could be categorical, those could be Gaussian. But when you think of making a policy more complex or more expressive, it can either be in the choice of going from a table to linear to a neural net, which is like the mapping itself. Or it could be in the choice of your probability distribution, right? And so, like, these are different mappings that go from S to the parameters of your probability distribution, but you can also make your probability distribution more complicated, right? So, like the simplest probability distribution is a Gaussian, which means that you're going to have a mean and a covariance over your actions, right? So, you're going to have a state that goes in. You're going to have a big neural net. It's going to have two heads. One is going to give you a mean. One is going to give you a covariance, right? And so that's the simplest probability distribution. You could have a slightly more complex one, which is categorical. Your state is going to go in. It's going to output, let's say you had like k different actions in a discrete distribution. You'll have a k dimensional output. right? And that'll give you the logits for a categorical distribution. And so the point here is that, and then you can go more complicated, right? So you can say, I'm going to have a more complicated distribution. I'm going to have a mixture of Gaussians, right? A mixture, are you guys familiar with mixtures of Gaussians? It is like k different Gaussians that you choose between. Right, so the difference is that this thing can represent more complex probabilities than Gaussian. And then you can have a diffusion model, which is like more complex even, so, yeah.
Wait, so the just a question, so is the reason that we output a distribution of actions, the action that we're outputting is not like, if, for example, we were outputting a torque, we don't, is the reason that we're outputting a distribution is because like the torque that we are outputting has some sort of error bound on it?
That's a great question. All right, so I think I have this on my next slide, but actually in most environments, you can actually show that there exists a deterministic optimal policy, which means that even if the environment is stochastic, you can show that you don't have to output a distribution. You can just output a single number, and there will exist an optimal policy, which is deterministic. But the reason you output a distribution is two reasons. One of them is you are trying to explore. So you're not trying to you're trying to collect data with some noise. And often you want to collect data around what your best guess is, right? And so it's kind of like a confidence interval, but to collect data. And the second is when you have, often you don't just solve a maximizing reward objective, you solve a maximizing reward plus entropy objective. And when you solve a maximized reward plus entropy objective, the optimal is not deterministic, it's stochastic, because you're trying to maintain some width, right? And that's to deal with noise. Okay. Right. So the important thing, which will come up in the next lecture, is there's two things. One of them is making the function more complicated. And the second thing is making the distribution more complicated, right? And so you can think of a policy as a combination of a function, which maps to the parameters of a distribution, right? So for instance, for a mixture of Gaussians, your function will map to the mean, the covariance, and the weights. For a diffusion model, your function is going to take in S and output like a vector field or a score function or a noise vector, right? And so in each of those things, it's like you're getting more and more complicated, but remember, there's something that maps from state to parameters of your distribution, and you choose a particular distribution. And that's how you define a policy. And you're typically going to choose a policy to maximize your expected sum of rewards. Right? And the whole study of this quarter is just going to be different ways to maximize that sum of rewards and optimize for the parameters of the policy. Right? And that's what we're going to do. Cool. I think we're at time. But I will see you all Monday, right? Thanks, folks. If anyone has registration problems, come talk to me. And there's donuts so that you give me good course evals. Yeah, they're for you guys to take, so please grab some. Hey, yeah, of course. Thank you. Okay. So yeah, I'm trying to do a few things. Hold on, let me stop recording before I get in trouble. We're trying to do two things. One of them is I'm going to try and move us to, the problem with this class is that it's just too small. And so I'm going to try and move us to CSE, which is 45% capacity, so we can go up to 50, and that'll make life better. And that I should know by then. So I think it'll work out. The other option is I feel like some people will drop out, they always do. And so let's give it like 1 or 2 days, and then I will go. Send me an email though. And I will be yeah, thanks. Hey. What's your name? Prabhav, okay.
Since I'm not in CSE,
yeah. You're Mackie?
We haven't
okay. Yeah. So here's the issue that I'm having right now, which is I'm happy to make the class as big as possible. The problem is this room only fits 35, which means I can only admit 38 legally to the fire hazard. So I'm trying to move us into a different room in CSE, which is 45, which will give us like 15 more enrollment. But right now we're like at capacity. They won't even let me enroll any. And so that's kind of the issue right now. So here's what I recommend. Like email me, maybe you've already emailed me. Okay.
But I will.
So just email me so it's in my mind. And give it a couple days. Maybe some people will drop. That'll open up a few, and then we'll probably move classes. That'll open up a few. That'll make life easier.
Thank you so much.
Yeah, of course. Yeah, yeah. Similar problem. Okay. Again, email me. And I will try to increase enrollment so that everyone can make it. But we have to move to a different class. And so I just need to find one. But just hang on. I would say just come to the Monday class. I should hopefully have it resolved by then. So, yeah. Simple. Okay. Remind me of your name? Did? Yeah, I think. I thought I admitted you, but maybe not. Okay. Again, it's like email me again once. Just send. You don't even have to say anything. Just do a ping so I like can filter. And then we will try to increase class capacity so we can. I will try to make it as high as possible. The only constraint right now is the room size. So I would say like 70% if I can move rooms or someone don't. And so that's so like this class is not that grading heavy, so it's like easy for me to expand capacity, but I just need to find it. So come by Monday, we hopefully make it. Were you guys next? Yeah. What's up? Same question. Yeah. Just email me again. You Sam, right? Okay. If you email me again, or like just send me a ping on your email, so I'll filter all the people, and I will get back to everyone on Ed. Are you on EdSTEM? No, you're not on EdSTEM right now because you're not registered for the class, right? I will try and get back to everyone with a bigger classroom by Monday. Cool. Yeah. Right. What's up?
So also the question between like the difference between like control and reinforcement learning.
Yeah.
It's like it seems very similar.
Yeah.
Like optimize like next semester where what? Is it just like the learning part?
It's actually like 5 slides later in my slides.
Okay.
But basically the main difference is that control will often assume that you know the model.
Yeah.
And reinforcement learning will often assume that you can only sample from the model. And so control will often assume you know the model, you know the gradients of the model, and